my work became progressively more focused on that broad area. And when Lancaster University in can't remember now, 2000 and something, quite recently anyway, opened its medical school for the first time, I left the Department of Mathematics and Statistics and joined the medical school. And since then, all of my work has been really, I think, best described as being at the interface between statistical methods and epidemiology. And it's based on my overall premise and approach to work that statisticians on their own can't solve public health problems, and public health experts on their own can't solve problems optimally. And by that I mean that epidemiologists can do good work without statisticians, but statisticians can sometimes help them to just add a bit of value to their work. So we're very much an added value discipline in the population health research space. And I hope this talk will basically reinforce that point of view. And although there's quite a lot of quite sophisticated statistical theory underlying what I'm talking about today, I'm going to keep the equations to a minimum and try to convey the essence of why what we do, going beyond routine textbook statistics, does add public health value to the research we do. And after my talk, I will be very pleased to answer questions. And if there isn't time after the talk, I'll be very pleased to receive questions by email. And if you don't know how to contact me, I'm quite easy to find on the internet. And if that doesn't work, then Cameron obviously has my email address, and I'm happy for him to give it to anybody who wants to contact me with any questions after the talk. So with that general introduction, I'll share my screen. And I hope that now is visible to everybody. Is that good, Cameron?
Yes, that's good.
Now, the title is not the one that Cameron advanced, but I hope you'll understand that I give a lot of these talks, and the underlying message is always the same, but sometimes conference organizers have to ask me to use a particular talk, and I confess that I forgot to redo the title slide to reflect the title that Cameron's advanced, and more importantly, the date. So this is not brand new work, and in fact, it is now published. And again, if anybody would like the reference to the publication after the talk, I'll be very happy to give that to them. But I want to start by just talking to this one picture, which really conveys the essence of what my group in Lancaster does when we're asked to help public health professionals design, run, and most importantly, from our point of view of what we're able to contribute, to interpret the results of surveys of various neglected tropical diseases in a variety of low and middle income countries. Most of our work is done in collaboration with agencies working in Africa, but we do also have projects in Southeast Asia, currently in Bangladesh and Sri Lanka, and we have also a connection in Latin America through a Brazilian research foundation, which does a lot of work in the favela slum communities of Brazilian cities. But here we are in West Africa. This is the country of Liberia. And what you can see in this map of Liberia is some colored circles. And the radius of those circles is proportional to the prevalence of a condition colloquially known as river blindness, formal name onchocerciasis, in rural communities throughout Liberia. And those empirical prevalences, I call them, are obtained by going into the location concerned of the community, enrolling a hopefully random, although it's hard to formally randomize it, but recruiting what you hope is a representative sample of the inhabitants of that village community, testing them for the presence or absence of onchocerciasis parasites in their blood, and then simply plotting the observed proportion of those people who test positive. Now, Two things immediately to say about the map are, firstly, that this is just a very small fraction of the number of rural communities in Liberia. And what we would like to do using these data is to be able to advise the people responsible for rolling out mass preventative campaigns to protect the communities against river blindness. We'd like to be able to advise them is what is the state of the onchocerciasis prevalence surface throughout Liberia. We obviously have some data directly on the communities that we've sampled. Even that is not perfect. It doesn't tell us exactly what's happening in those communities. But rather more ambitiously than using those data to tell the authorities what we think the prevalence level is in those particular communities, can we actually use them to find out what's happening in the remainder of the country where we don't have any data? So on the face of it, that sounds like a very ambitious goal, but there are ways to make it a feasible goal, as I will discuss. But from a statistical perspective, if we start with that declared aim of saying, I want to map the variation in prevalence throughout Liberia so that we can inform the appropriate priorities for treatment and the appropriate strategies for treatment, which differ according to how high the prevalence is, what do we need to do? Well, we need to answer three questions. And often, as a statistician, we find that the first two questions have already been answered for us. But I will say later in the talk that it is certainly desirable that we are consulted before those questions have been answered. So the first question, how many samples do they need to take in order to get a usefully precise answer to that question? And in this case, as in many of the cases we work with, and for reasons I completely understand and sympathize with, that decision's already been taken. These are the data. That's what you've got. We can't afford to get any more. And if we'd been able to get away with less, it's too late. We've already done it. Secondly, a more subtle question is, where should you put those samples? Or again, I should really say, where should you have put those samples? Because again, this is something I don't need to emphasize to a Malaysian audience. But in working in a comfortable office in a wealthy country, it's easy to tell people how to design experiments optimally. But when resources on the ground are limited, you have to be pragmatic. And I don't know exactly why these locations were chosen, but I'm sure they were chosen partly because the field epidemiologists involved have had many tasks to perform. And very often in visiting a community, they would be there for multiple reasons. And some of these data would have been collected opportunistically because there was a field epidemiologist available to do the data collection for other reasons. And so at the moment, I simply want to say that the number of these dots and their positions does affect how we should analyze the data. And in particular, both of those things affect how precisely we can answer this question. And then this is what the statistician typically spends most of their time doing, is how should we analyze those data in order to answer the public health authorities' question. So my colleague Emanuela Giorgi and I have written a book about this, which appeared last year. And I will leave it to others to decide whether that's a book that you should devote any of your time to reading or not. But if you do want to get into the real detail of the statistical methods underlining what I'm talking about today, that is a place to look. If, however, you are more interested in how these things work in their application, then this paper, which has now appeared and which I can give the exact reference to if needed, basically is the written published version of what I'm talking about in the remainder of this lecture. So that might be a useful place to follow up from the talk, if you wish. Now, why are we going to use geostatistical methods? So I really should first say, what do I mean by geostatistical? So if I go back to my map, a classical statistical method applied to these data might be something like the following. We want to know what the average prevalence is in Liberia. We've got some data, so we've got some observed prevalences. So if we wanted to know the average prevalence, a natural thing to do is to take the sample mean of the observed prevalences. And if we wanted to know how precise that estimate was, we could look up our statistics textbook of choice and find that the standard error of a mean can be calculated, and we would quote an estimate of the observed sample mean plus or minus 2 standard errors as a confidence interval for what we thought the true prevalence was. Now, nowhere in that calculation would you be explicitly using the locations of the data points. And a geostatistical method is one in which the locations of the data points play a material role in the analysis of the data. Okay? So the question is, why are geostatistical methods important for answering these kinds of questions? And the simple answer is that the kind of classical survey sampling methods I've indicated for calculating a sample mean and its standard error are generally inefficient when the data are spatially correlated. Now, what do I mean by spatially correlated? Again, we go back to the map. The size and color, to remind you of these dots, corresponds to the level of observed prevalence. And what you can see is that the colors, which I think are the visually most striking feature of the map, are not randomly scattered through Liberia. If you look at the red dots, which are the high prevalence areas, there are none at all down here, a lot quite close together here, and 1 or 2 in other places. And where they are isolated, then they're typically next to not a blue dot, which is the lowest category, but a brown or a yellow or a green dot, which are the intermediate categories. Down here, you have a very obvious phenomenon that onchocerciasis has typically very low prevalence along the coast. There must be something about the local environment here that makes it high risk, but generally speaking, if all you knew about a location in Liberia was that it was along the coast, you would predict low prevalence. So this phenomenon is called spatial correlation. In other words, it basically just says that once you've observed a value of something, it doesn't just tell you about what's happening at that place. And what I mean by nearby will depend on context. It could be that near within, let's say, 10 kilometers. It could mean within 100 kilometers or somewhere in between. And we have to estimate those properties from the data. But a spatial correlation basically says, and this is the second point on my, why I use geostatistics methods, is statisticians call this borrowing strength. The fact that a datum associated with one particular location has value in predicting what's happening at nearby locations is sometimes informally called the first law of geography. And the first law of geography says that all things are related, but close things tend to be more closely related and more similar than distant things. And we exploit that in order to get operational performance of our predictive methods, which is really sometimes, as you'll see, very much better than classical survey sampling methods that don't make use of the information in the geolocations of your data points. So here's a simulated example to show you of the kind of increases in precision that you can get in what I think is a not unrealistic situation. So here is a hypothetical square region of a country of interest in which the true underlying prevalence of disease is indicated by that color coding, with white being the highest and red the lowest, and the area average prevalence is 41.7%. So I now simulate onto that piece of territory some data. I've put down some locations where I'm going to measure prevalence. And again, I've coded the values I get according to the size of the circle, and you can see that unsurprisingly, the large circles tend to occur on the white and pale yellow, and the small circles tend to occur on the dark red. But it's not totally predictable. We have to actually do some analysis. And if I do the classical survey sampling analysis that I described a couple of minutes ago, the sample mean of the values in those circles is 41.3. Not a bad estimate. It happens to be almost spot on. The standard error, or rather plus or minus 2 standard errors, is plus or minus 8.6. So that may be a useful answer. But if we do a geostatistical analysis, and I haven't shown you how we do that yet, but I will, we get 41.6, which is almost identical as a point estimate, plus or minus 1.4. So this is a very substantial improvement in precision. And amongst other things, it means that if A, resources are scarce, and B, 8.6 was an acceptable plus or minus, then you could have saved a lot of money, because by doing geostatistical analysis, you could have achieved that 8.6 with a much smaller sample. Conversely, if resources are scarce and you are disappointed to find that plus or minus 8.6 is too imprecise for your needs, then help is at hand, because without collecting any more data, you can do a lot better with a geostatistical analysis. Now, this is simulated, but we'll come back to some real data real soon now. The take-home message from the simulation is that by exploiting spatial correlation, you can achieve more precise prediction. Now, this is a schematic of the model that we use, and you really don't need anything more than this to understand the idea of geostatistical modeling. Because typically, when you're trying to understand variations in prevalence over a geography, if, as is the case with river blindness and many other neglected tropical diseases, this is an environmentally driven disease, because it tends to have high prevalence in areas which are suitable for the vector to breed, and low prevalence in areas which are unsuitable, and you can measure those factors through environmental covariates. And I have a question from Mitzi, so please feel free to ask it. No? Mitzi, you had your hand raised, I think. No? Okay, we'll carry on. But I'm very happy for you to interrupt me as long as Camarul is happy for you to unmute yourself. Otherwise, we'll get to questions soon enough. So, I want you to imagine that you're running from west to east in a country where you're trying to find out about an environmentally driven disease. And as you walk from west to east, you notice that it's getting hotter and it's getting wetter. And you have an entomologist with you, and the entomologist knows that as it's getting hotter and wetter, you're more likely to find suitable breeding conditions for the biting fly that transmits river blindness. Every so often you come across a community and you take a sample, just as they did in Liberia, and you look at the observed empirical prevalence of river blindness in your sample. And you find that just as the entomologist would have predicted, as you walk along this west to east transect, you generally get increased prevalence, but not strictly, because there are other factors that we haven't measured or haven't noticed in the environment, and they might be due to the social behavior of the communities concerned. There could be many reasons why this environmental gradient, which is the solid line, is not a perfect predictor of prevalence. Right. Now, we wouldn't expect our data points to lie exactly on the line, even if we had got the correct environmental predictors, because we know that when we take a sample from each community, we will have statistical variation due to the fact that we have sampling error. We'd like to know the prevalence in a complete population. All we have is the test results, positive, negative, in a sample. But our textbooks tell us how big that statistical sampling error is. And so we can look at that statistical sampling error and ask the following question. I've just indicated it in one point here, but if we applied that sampling error formula to all of the circles and said, does that look compatible with how far away the data actually are from this solid line? And if the answer is no, it's too big, which it is here, then there must be something else that we've not measured that's explaining that additional variation. So the dashed line is the something else that we've not measured. And the way statisticians deal with things they've not measured is they call them random variables, and they add them to the model so that they do not report spurious precision in their findings. And so what we have here is unobserved random variation, which we can model statistically, exploiting the fact that this phenomenon is spatially correlated. And so although we don't have direct measurements of it, we can estimate it and incorporate it into our predictions by looking at the way in which these circles deviate from the solid line. And in particular, we have this tendency, even in this very small sample, to have a run of negatives here, a run of positives here. And so our best guess is that the underlying unmeasured variables are making things a bit more risky down here than the solid line would have predicted, and a bit less risky up here. And we can attach measures of uncertainty to those predictions. So here's a case study of how we did this, looking for another disease, lower, or colloquially known as eyeworm, in Cameroon. The setup is exactly the same as Liberia, whereby samples have been gathered opportunistically, and I'm showing them on a map as color-coded circles. And as in Liberia, they show very strong spatial correlation. The very high-risk red dots tend to be rather clumped together, but they are intermingled with lower risk other colors. So it's not entirely trivial to map the disease countrywide. Okay, we want to do this not because we're interested in lower per se, but because if an area has high prevalence of lower, then the standard treatment for protecting people against river blindness is potentially unsafe for individuals who are carrying high levels of infection of both parasites. If you're heavily co-infected with lower parasites and river blindness parasites, you are at risk of suffering a severe adverse reaction from the drug that would normally be considered a very safe prophylactic treatment for river blindness. So we don't want to be going out treating everybody for river blindness if in fact we're working in an area where some of those people are at high risk of having a severe and possibly fatal reaction to the drug. So we really need to map eyeworm, lower, as an adjunct to mapping onchocerciasis, which is the disease we're really interested in. Now, what will help us to do this is that we know that, again, we're dealing with a vector-borne disease, and if we have information on greenness of vegetation, which we do from a satellite image, and if we have information on height above sea level, which we do from satellite imagery, then we can actually use those covariates as part of our predictive model for prevalence of lower countrywide. And we have a very specific goal in doing this, because the WHO have decreed that if you want to administer mass treatment for protection of a community against river blindness, you can only do so in areas which do not have a prevalence of lower greater than 20%. If you're in a high risk area, in other words, one where lower prevalence is greater than 20%, you must not treat everybody indiscriminately with Mectazan, which is the drug of choice. You have to take additional safety precautions to protect high risk individuals, and that is expensive and it's difficult, and it's a major obstacle to rolling out the river blindness program. So we're going to use geostatistical methods to answer WHO's policy relevant question. Can we map whether or not this is a high risk area? We start with a very simple idea of simply fitting a regression model, in this case a logistic regression model, and we plot what we observe from our sampled villages on the y-axis and what the logistic regression predicts on the x-axis, and you can see that we are getting a useful relationship. That's quite a good association. It's a very useful predictor, but you can also see there's a very considerable degree of scatter. So we can certainly make a prediction using logistic regression, but this is a kind of indication of how imprecise it is. Now, if you move to the right-hand diagram, we're now adding that dashed wiggly line. We're adding the spatially correlated random process that gives us predictive power over and above the measured height above sea level and greenness of vegetation. And you can see that it's a much tighter association. So the difference between these two pictures is the benefit that you've got from adopting a geostatistical rather than a classical approach to analyzing the prevalence data. And as a result of doing that, you can produce a map which I would argue directly addresses WHO's policy criteria. Because what this map shows you for the whole of the country is the probability that each location on the map does or does not exceed the 20% prevalence threshold above which you need to withhold mass treatment with mectizan. Now that's a useful map because it tells you that in all of these yellow areas, the probability of you exceeding 20% threshold is pretty close to zero. And you can see that that's extending way beyond the observed points where we have actually got data, which are the blue dots. And that's because the covariate information is sufficient to tell us we may not have any data here, but purely on the basis of its height above sea level and the greenness of its vegetation, we think it's safe. So you can go ahead with treating onchocerciasis in these areas. At the opposite extreme, red for danger. The red areas are those where we're highly likely, 80% or more, and if it gets down to the very dark brown, 95% or more probability that local prevalence exceeds 20%, and it would not be safe to roll out mass treatment with mectizan indiscriminately. And from my point of view, at least as importantly, the pink areas tell you where you honestly don't know. Pink is a 50-50 call. And as a statistician, and I'm sure many other people who are not statisticians would agree with this, if you don't know the answer to a question, it's better to say you don't know than make a wild guess. Now, at every point in this map, I can give you my best guess at prevalence, and that map would divide into areas where my best guess was above 20% and where my best guess was below 20%. But in these areas, my best guess is precise. I'm pretty confident about it. And in these areas, my best guess is precise. I'm pretty confident about it. But in the pink areas, my best guess is a wild guess. And I think it's better to acknowledge that than to produce simply a map of prevalence and assume that people treat it as if it was the truth. And this is the best way I know to convey uncertainty honestly in statistical maps. Don't map prevalence, map the probability that prevalence is in a range that would be of public health concern for the question at hand. A little aside on where you should put your points if you really are given the opportunity to do so. Again, my synthetic surface, I could have attacked it by a random sample, and many textbooks would tell you that's a good thing to do. It certainly has the advantage of avoiding subjective bias, but it's not efficient. And if instead you'd sampled the data like this, you would have been able to get more precise mapping of the local prevalence. And this is again tied up in a way that I haven't got time to go into in detail with the phenomenon of spatial correlation. Because in a random sample, when you by chance get points very close together, because they're spatially correlated, in essence, they're duplicating the information. So they're wasting effort. That second point of that very close pair near my hand there is essentially a wasted sample point, because the nature of the underlying surface is such that I don't need that second sample point to tell me that that point was yellow. So that's the principle whereby we recommend in our own work spatially regulated sampling. It doesn't have to be as rigid as the one here. We usually like to preserve an element of randomness so that we can appeal to randomization theory if we don't need to, and we have trouble fitting a parametric model. But the basic principle of spacing your sampling points out more regularly than they would be in a random sample is a very sound one. There's a lot to be said, if you can, when you're doing prevalence surveys, for running them adaptively, meaning that you collect some data, you analyze it, and the way you analyze that initial data will inform where you need to take more samples. And the best way to illustrate that is to say, if I gave the teams in Cameroon enough money to go and take another 100 sample points, would they take any more out here? I would say don't bother. Would they take any more here? I would say don't bother. I'd say take them here, because this is where we don't know what's happening, and the extra samples can be devoted to reducing that uncertainty. Okay, so that's the basic message in a nutshell, and I'm pretty much, I think, exhausted my time camera rule, and I'm very happy to stop that there, or if you prefer, and I really want you to tell me what you prefer, I could give you a second case study of lymphatic filariasis in Ghana, but the take-home message is the same one, that if you design the study well and use geostatistical methods to analyze it, you can get very substantial, sometimes by an order of magnitude, gains in efficiency over the methods that current NTD controlled programs are using. And what the team is currently doing in Lancaster, we have 3 very good postdocs, 2 academics, myself and Emanuele Giorgi, and several research students. We're working on developing and applying these methods in the context of a range of neglected tropical disease, mainly, as I said earlier, but not exclusively in Africa, and supported by a number of agencies, including the Gates Foundation, the WHO, the Task Force for Global Health in Neglected Tropical Diseases in Atlanta, Georgia, and Evidence Action, a charity working primarily in East Africa. So I think Cameroon, actually, that's quite a nice place to stop, and I'll take questions.
Yeah. I think you can go on. Take your time, Peter.
Okay,
I think it's good to do. Yeah, right, definitely.
I can do that. Okay. Right. So this is the my second case study, and this is the country of Ghana, and this is LF prevalence. Now, one of the vagaries of screen sharing is I can't see all the headings on my screen. So if you'll bear with me, I'm just going to re-find my place in my slides. That's what I wanted. Yes. Okay. So now you can see the title. This is a second case study of lymphatic filariasis in Ghana. So having said that, I can go back to my full screen mode. Right. Now, again, this is an area where we work in order to tell field teams whether they have or have not got enough evidence to reach a decision on a WHO moderated policy implementation, namely elimination of lymphatic filariasis as a public health problem. And the agreement that's been reached over a number of years by a number of people who know a lot more about lymphatic filariasis than ever I will, is that in directing resources to reduce the prevalence of lymphatic filariasis in a particular region, if you can establish that you've got the prevalence limit below 2%, then you can declare that that is no longer a priority public health problem. It doesn't mean you will not help people who are unfortunate enough to suffer from lymphatic filariasis, but in terms of the optimal use of scarce resources, the country may decide it has other priorities. So what we've done is we've taken the availability of historic data on lymphatic filariasis in Ghana to run a simulation exercise of how our methods can be used to determine whether a country has or has not reached their elimination target. So the idea is we take data from Ghana that were collected before there were any interventions that had been made to reduce the prevalence of lymphatic filariasis. And this is what it looked like. This was what Ghana looked like with regard to lymphatic filariasis prevalence before any intervention efforts. And you can see that there's a very strong geographical pattern to the prevalence, that it's very high, very occasionally above 50% in the southern coastal area and in the northern area, and it's generally lower in these intermediate areas. And the goal is to get all of the country down into the blue zone, at which point it will no longer be a priority for scarce public health funds. So what we're going to do is we're going to actually model the progression from baseline to near elimination status. We're going to actually take those baseline data, fit a model to them, and then we're going to adjust that model so that the prevalence goes downwards, but it doesn't just go downwards by a constant amount. It goes downwards relative to its initial value, because if you start at 50%, you've got quite a long way to go downwards, and you will have had quite aggressive interventions. Whereas if you start at 2%, you're actually already there. You're not going to make much change, and you had less aggressive interventions. But we basically come up with an idea of what we think the country would look like if, on average, it was just about at the elimination threshold. And we will then apply our methods, as we did to produce the lower map in Cameroon, to map whether, with high probability, at least 95% probability, that particular part of Ghana has achieved the goal of prevalence being less than 2%. So it's the same basic idea as before, which is that there is a target. We can't say for certain whether that target has been achieved, but what we can do is quantify the likelihood that it's been achieved, and thereby whether the country as a whole, or perhaps only certain parts of the country, can happily declare that they've eliminated LF as a public health problem. And what I'm going to do is I'm now going to very explicitly compare what we do with what the WHO current guidelines say should be done. So here's our best guess at what Ghana looked like at baseline when we applied our geostatistical modeling to the data that I showed you on the previous slide. And I want to emphasize a practical point here, which is that although our models treat Ghana as a spatial continuum, and this is our best map of local prevalence Ghana-wide, operational decisions about treatment are made on areas, are made on administrative regions. So the right map just shows the same information, but at a district level, because once you've modeled the spatially continuous surface, you can deduce the properties of whatever aggregation, in this case to administrative districts, concerns you. And whether you prefer this map or this map is purely a matter of choice. They're both preferred using the same methodology, and they have the same interpretation. Similarly with our predictive probabilities. And there is a bit more of a difference here, but again, the principle is the same, that what this map shows is our best prediction of the probability at each place on the map that local prevalence exceeds 2%. So we're pretty certain it does here, we're pretty certain it doesn't by the Big Lake, and we're pretty certain it doesn't in 2 areas, but there are these areas intermediately where we're really not certain. This is the same at a district level, and what we mean here is that the district-wide average is below 2%. There could be locations that are high, but if the district-wide average is below 2%, that's what the WHO goes by in declaring that district as being having eliminated the disease as a public health problem. So then, using our model and our knowledge of what's gone on since baseline, we now produce predictions that say we think this is what Ghana looks like with respect to LF prevalence at a point where the countrywide average is 2%, which is the elimination threshold. And again, you can look for spatial continuous maps on the left, or spatially aggregated maps, choropleth maps on the right. And we think that this is what the true state of the country is. So in other words, we think there are still some residual areas in the north where we're fairly certain that it's above 2%, because they're red, but notice they're not bright red anymore, they're orange. So our best point guess may have been high, but we're sufficiently uncertain that we're only going to cover these areas, districts orange or yellow. Similarly, on the south coast, we've got a lot of dark blue areas, which we're happy to say we're pretty much sure are eliminated, and we've still got these uncertain areas in the middle. So now this is the results slide. This is essentially the last slide. What do we do with these things? Well, what we do is, because we have simulated this surface, we can now interrogate it using our methods of geostatistical analysis and using the WHO guidelines, which are published in a manual that the public health authorities use to decide on the basis of their observed data whether or not they've achieved elimination. And the cross on each of these pictures is in the same place, so I only have to explain it once. The cross is saying, what is the positive predicted value of the WHO guideline? And what that means is, what is the probability that a district that truly has achieved the guideline will be declared as having achieved the guideline. And it's quite good, it's 95%, right? On the bottom axis, we've got 1 minus the negative predicted value. Now, the negative predicted value is the probability that an area that truly has not achieved elimination has indeed not achieved elimination. And that's not so good. You can see that it's something like 30%. So there's a lot of room for improvement in terms of getting good prediction of both areas that are not eliminated and areas that have eliminated LF. Now, the curve is a range of variations of our method. And the reason why there's a range of variations is that what we do is we don't say yes or no, we say the probability of UNAID transmission is such and such. And we can always increase one probability, say the positive probability, at the expense of decreasing the negative probability. We can't simultaneously increase both. So you can either say we are actually going to be at 0%, okay, on one axis, right? And the left-hand origin here basically says we're always going to make the same decision. So we're not really doing anything very intelligent. Where we'd like to be is in this top left-hand corner, because the top left-hand corner means we're getting 100% positive predictive accuracy. Oops, sorry. And also, bearing in mind that this left-hand axis, this bottom axis is 1 minus the negative predictive value, we're also getting 100% negative predictive accuracy. Well, it's easy to get 100% negative predictive accuracy. You just say no all the time. But then you got no % positive predicted accuracy. So you can always be here, and you can always be here, but you'd like to be here, and you can't be here because there's no free lunch. But the curve shows you, depending on where you set the threshold in your algorithm, how close you can be to this ideal point. And basically what you want to be is as close to that top left-hand corner as possible. And you can see that our curve certainly dominates the cross. Now, whether you think it's best to be here, or here, or here, or here, or here, or here, depends on what cost you put on an incorrect positive prediction or an incorrect negative prediction. But basically, you can win on both dimensions by quite some margin. Now, here, the same applies. The curve beats the cross in both directions simultaneously, but by a much smaller margin. And the reason for that is we're basically now reducing, for our method, the number of samples by a factor of 5. We're still using the original number of data points for the WHO method, that's the same. But we've reduced our sampling effort by a factor of 5, and we still beat the WHO guideline. Here we've reduced it by a factor of 10, and now we lose out to the WHO guideline. Sorry. There you go. So we're pretty pleased with that result, but clearly there's a limit to how much you can achieve. Now, in fact, in this case, there might be an argument, and there might be an argument more generally for saying, if you save money by sampling fewer schools, which is how these things are typically done, maybe you could sample more children per school. So in this bottom middle part here, I've said, okay, I've reduced the number of sampled schools or communities, in this case it's schools, by a factor of 5, but to compensate, I'm sampling 5 times as many children per school. So the total number of children is the same for both the cross and the curve, but they're concentrated into fewer schools. And that's often operationally cheaper because then you don't have all the travel time. And now you almost recover the performance of the full method. And even with reducing the number of schools by a factor of 10, if you do the compensatory increase in the number of children, you get a very much bigger improvement in performance. Now, this might not be possible because you will all know that there are a limited number of children in any one school, particularly in rural communities. So it may be that there are not enough children in each school to achieve this. But I would say that this picture alone is the one that shows you that we're not dealing here with just a few % of precision. We can have an order of magnitude shift in the field sampling effort and still do better slightly than the current method. And depending on the resource constraints, you can optimize between the number of children, the number of schools, the total cost of the survey, and optimize the geospatial prediction. So that really is the full story. just to wrap up, the methodology that underlies all this has been developed over about 20 years by a lot of people, and there are a growing number of case studies now showing how it can be used in tropical disease Epid. All of the analyses run on a standard laptop using open source software that we've written at Lancaster, and basically our group very often operates as a sort of remote advice service, providing backup to local users. I think that's as much as I want to say, except perhaps in this very last slide, statisticians talk a lot about efficiency because it's what they learn in school and it's what they're good at. But it does seem to me that in low resource settings, efficiency considerations really are paramount. And so you can't afford to analyze hard-won data inefficiently. The key message is that exploiting spatial correlation gives you very substantial gains in efficiency, and it seems a shame not to have those gains. I very much want to emphasize our approach where how we map our results is related directly to the policy decision thresholds that apply in the particular context. So just saying, here's my best map for prevalence is not a good thing to do, in my humble opinion. You want to know how certain are you of what's happening on the ground, where it's critical to what you do as a result of what's happening on the ground. And our group is moving increasingly towards devoting as much effort as we can to capacity building rather than further development of the research methods, which are now pretty mature. So we do have a 2-day workshop that we have run both in country and remotely on a number of occasions, and would be very pleased to discuss with potential audiences whether there would be an audience for a version of that workshop directed at a particular country or at a particular community with interests in particular diseases or public health problems. So thank you very much for your attention, and I'll be happy to take questions.
Excellent presentations by Peter. So yes, I think there's if you can see the chat box, Peter, there's one question from. All right, yeah, it's not really a question. I think that's more comment by Vina Tan. So she said that thank you, Peter, for opening my eyes to geospatial applications. Not a statistician, but very applicable to her work. So yes, excellent. So thank you, Vina. Yes. Any questions from the floor? Yes, please go on. Yes, Bakri is the alumni from Lancaster University. If you remember him.
Indeed. Yeah. Hi.
Go on.
Why don't you unmute, Bakri, and tell me your question. You say it may be difficult to get the sample for option 2. Which was option 2?
Hello, Prof. The option 2 is about the hello, Prof. Hello, Peter. The option 2 is about you are taking each location. This might be difficult to get to that location. What is your suggestion?
Yes, I must admit. I must admit that I prepared that slide to really visualize the difference between randomness and spatial regularity. But in fact, of course, you need to sample from communities, and communities do not sit on a lattice. But the same principle applies, that if you have a map of where the potential sample communities are, then you want to sample those by a mechanism that's objective. It's randomized so as to be objective, but by constraining it so that you do not sample close pairs, you get gains in efficiency. But they're less extreme than they would be if you could sample literally anywhere in the continuum. So I think a better slide would have been to show you how in practice, when we're given a complete map of communities, we thin them selectively so that we end up with a subset of communities that cover the country in a more regular than random fashion. And I should also say that although that's the ideal thing to do, the bigger gains do come from the geospatial analysis. And so we're very happy to analyze data that haven't been designed specifically with this purpose in mind. because the gains at the analysis stage are usually still very substantial and worth having. If you really can design from scratch, it's advisable to induce some degree of spatial regularity in the communities that you sample. But a lattice would clearly not be a sensible thing to tell people to do in this context. Thanks for that, Bakri, and that clarification.
Peter, I've got questions. I mean, all your examples were related to infectious diseases. And how is this geostatistics applicable to non-infectious diseases? For example, cardiovascular disease. Have you had any experience in that?
Arguably, it's more applicable. Although these are infectious diseases, they're vector-borne rather than direct transmission. So you can usually capture the spatial patterns by a combination of environmental covariates and the idea of a spatially correlated stochastic process. Whereas if you're dealing with direct transmission, such as Ebola or COVID, then arguably your models should include something to do with transmission mechanisms. Now, in fact, even although that's the case, if your goal is wanting to understand what's happening now, rather than to predict where the epidemic is going, then these methods still work pretty well. But what they don't necessarily work so well at is doing very detailed forward projections of the kind that we've seen 100 of during the COVID epidemic, because they don't have within them any biological transmission mechanisms built into the model. They're purely statistical models. You can use them for short-term forecasting quite well, but they're not mechanistic models. So for non-communicable diseases, I think they're at least as well suited as they are for the kind of setting I'm working in. The difference, I think, is much more the following: that the methods I've been talking about were designed originally in a very different context, but a very similar context in the particular sense that they were trying to find out a spatially continuous phenomenon from sparse, spatially discrete data. The original context was actually in gold mining in South Africa, where you want to basically find the gold, and what you have to do is dig exploratory holes and see if you find any gold there. And if you do, you assume there's probably more gold nearby, right? Now, in the epidemiological setting, in wealthy developed countries, if you've got complete disease registers, then the kind of models that I'm talking about have less to offer. They're not unhelpful, but they have less to offer, because what they're really good at is making the best of spatially sparse data on health outcomes in combination with spatially abundant data on risk factors, environmental risk factors or social risk factors. For example, I have used them in a UK setting where the risk factors are actually indices of social deprivation, which are available from the census as a background map. And again, you use it as a covariate because it does partially explain the health outcome. But it's when your health outcome data are incomplete and you want to combine them with much denser covariate information that the methods tend to give you the best payback.
All right, thanks, Peter. I think maybe we can. Maybe you can briefly answer a few questions in the chat box. I'm not sure whether you want to read or you want me to read the questions to you, Peter.
Yeah, you read them, Kamarul.
All right, okay. So there's one question from Shubhas from the Institute of Public Health. So he said that he noticed that there are quite substantial amount of points used in the examples, your examples. Would this means that your method is better suited with administrative data rather than sending a research team to sample sites for sampling purposes? As for a survey research, that may be limited due to the number of sites, due to cost. So they have, they can't samples a lot. How will you respond to that, Peter?
Yeah. It's it depends what you mean by a lot, because let me give you a very specific example. When I did the Ghana LF case study, I don't think I need to show you the map again, but Ghana was divided into districts, and the districts were the units that were wanting to answer the question, has this district eliminated LF, yes or no? The WHO guidelines required them to sample 30 schools per district. right? Now, our methods meant that they could indeed have done better, even if they'd only sampled 6 schools per district, if they'd used our methods, right? So one of the main points of our methods is in resource-limited situations, the geospatial analysis can materially reduce the number of sites you need to get an efficient answer, right? And even if you went down to 3 per district, we still only did a little bit worse than the WHO. And we could do better if we could increase the number of children per school. Now, very important, however, to say that if you were interested in a particular district, the data from your district alone, your 3 or your 6 schools, would not have been enough to give you a decent answer. It's the fact that what's going on in neighboring districts is predictive of what's going on in your district that makes the methods work. So the number of points you need relates quite directly to the scale of the spatial correlation in the outcome that you're trying to map. And these methods work best when the scale of the spatial correlation is large, right? And therefore, for a given area, you don't need many data points. But obviously, the wider the area you're trying to cover, the more data you need. But it may be that at an operational level, the operational teams within a district have to do an affordable amount of work. But it really, there isn't a universal answer. If when you do this stuff, you find there isn't any spatial correlation, then there's no benefit to doing a geostatistical analysis. But most of the things that I've looked at in my career, there has been spatial correlation, sometimes to a very considerable extent, sometimes not so considerable. And equally, if you can capture the spatial variation in covariates, great, you can fit logistic regression models. So I don't think there's a universal answer to your question. It's a very fair one. And as I said also earlier, that if administrative data is routinely available and is comprehensive, then again, relatively simple statistical methods will usually tell you what's going on, because in effect, you've got the whole population in your data set. But it's definitely, in my opinion, where the data, the health outcome data are sparse, that we can do the best possible job. But if those data are both sparse and completely random with no spatial structure, then we can't add much value.
Right. I can't run away from these questions, and in fact, there are 2 people asking. Yes, COVID-19. Any role of geostatistics COVID-19?
Absolutely.
You did mention it just now,
but I think there's a certain poetic justice. I think there's a certain poetic justice that at a time when the UK, to its great shame, is proposing to cut its overseas relief budget, it finds itself having to deal with a very large epidemic with very sparse data. It finds itself in the situation that low-income countries have suffered for many decades with diseases that in principle could be treated, but they didn't have the money to do so. And so, in fact, I am personally using geostatistical methods to help understand the COVID epidemic in the UK in 2 studies. One is conducted by Imperial College London. It's called the REACT study, and it made headline news only this week on the national radio, because what we have found by doing a geostatistical mapping of a randomized sample of patients who were tested positive and negative for COVID infection, that in the last 2 weeks, the average prevalence of COVID current infection in England has gone, in some small areas, which is where the geostatistical element becomes important, down by more than 50%, whereas in others the reduction has been very small. So we use geostatistical methods precisely because the UK does not have money on building surveillance systems when there wasn't an epidemic, but that's a whole other story. So for COVID in England, we're exactly what individuals randomly located throughout the country for COVID, passed the data to Lancaster, and we applied our mapping methods. The second study we're doing is actually, in my opinion, a less robust study because it's based on self-reported COVID symptoms. And whilst we can look at the changes over time in those, we are unable to quantify the bias that's induced by the self-reporting. So in particular, if you want to sort of Google the REACT study, capital R-E-A-C-T, and COVID, it'll come up and you'll have access to reports which include, look for round 7. That's the which changing prevalence.
All right. Peter, thanks very much. Thanks very much for your time. It's definitely way over our allocated time, and I mean, it's going to be rare to have you presenting at our webinar, and we are very, very privileged to have you. Thanks from all of us for for agreeing to talk in our webinar, and I hope we can see you soon, and perhaps for after this webinar, if anyone would like to communicate or in contact to contact you, then I have the email from the Peter email, so I can give to anyone who is interested to get in touch with Peter after this. So thanks again, Peter. Have a nice day. Stay safe, and send our regards to all the friends at Lancaster. And bye-bye.
Thank you, and it was a great pleasure talking to you all. I hope it's been of some interest. Thank you. Bye.
Thank you. Bye.